welcome to this edition of the Satellite Image Deep Learning video podcast series. Today, I'm talking with Cesar Aybar. Cesar has just completed his master's degree at the University of Salzburg, and next year will begin his doctoral studies at the University of Valencia. His present work includes the automation of satellite image pre-processing using deep learning, the construction of datasets for Earth observation, satellite image quality assessment, and the development of cloud detection algorithms. He led the creation of CloudSEN12, the largest open dataset for cloud semantic segmentation of Sentinel-2 imagery. I give you Cesar.
Hi Cesar, great to have you on the show today. How are you?
I'm very fine, thank you for the invitation.
Yeah, very excited to hear about CloudSEN2. I think that's the right name for it. Would you like to give us a quick introduction to the dataset?
Okay, sure. Well, we basically construct a dataset, and as you mentioned it, we call it CloudSEN12. The main goal of this dataset is quite simple, is help in the construction of new algorithms for cloud detection, and more important than that, cloud shadow detection in Sentinel-2 images. So, okay, I think it's important to understand that cloud detection is not a trivial problem, especially in the remote sensing field, and specifically for Sentinel-2, because if we compare Sentinel-2 with other sensors like popular sensors like Landsat 8 or Landsat 9, they come with thermal bands, so it makes sometimes a bit easier to detect clouds. But in Sentinel-2, in some environments, since that you don't come with these thermal bands, it makes quite hard. For instance, it's in my mind right now, the Amazon rainforest. I think if you try to create a composite with Landsat 8, it will work more or less fine. But if you're trying to do this with Sentinel-2, it will be a disaster. So our hypothesis with CloudSEN12 is quite simple. It's like we think that if we are able to create a large data set, large and diverse data set, it will help dramatically in the detection of clouds. And also something quite important for us is ensure the quality of the labelings. So we are able to do these things that we construct a really robust labeling protocol.
Right. So
create a data set.
Was there a lot of experimentation involved in establishing that protocol, or was it pretty straightforward?
Yeah, well, design the data set, I think was the first thing in our mind, and this was clearly explained on the paper. And also we add some experiments after create the data set, because, okay, now that I have a large data set, we thought that it will be enough for reach the state of the art or surpass the state of the art. And this is something that we were able to achieve with the data set. Yes.
Fantastic.
If I can share my screen, I can show you. So, yes, before to start talking about this, is like maybe for people that is more computer science oriented, when I refer to cloud detection, is in fact a semantic segmentation problem, right? Where the input data is a level 1C, and it will pass for a model, and it will try to create these semantic classes. And for us, the semantic classes are these clear thin cloud, shadow. So we have the Sentinel level 1C, and it will pass for a model, and we will try to predict if one pixel is one of these classes. Okay, so this is more or less the previous, spatial cover of the available cloud detection dataset for Sentinel-2. And I think you can clearly observe that there is a bias for Europe, and I think it's quite obvious to know that what about if you try to extrapolate or try to train a neural network for a global scale? Like, it's quite obvious maybe to think that the algorithms, it will not work very well for those regions. So we pass from this extension from this new one. So as you can see, with CloudSEN12, we are more close to cover all the different landscapes around the world. And something quite interesting about CloudSEN12 is like every point that you can see in this map, in fact, represent 5 different images. So this previous datasets is only cover one image, but with CloudSEN12, we also cover temporal information. So, and we put a human in the middle, in the loop, because we want to ensure that we always come with a cloud-free up to a cloudy image, because in that way we are offering to the user as well a good balance between the classes. Because this is another problem that we also observed in the previous data set, is like you have a good data set, a large data set, but the 90% of the data set are clear pixels. So, and just the 1% is closed shadow. So it's impossible that you train a good neural network when you have a huge imbalance in your data set. So it was hard to do this because we have to do it manually, but no matter the point that you can see in the Cloud Free and the Cloud, as I mentioned it. So something quite interesting that also we do with CloudSEN12 is like we offer 3 different types of labels. Like we have this high quality or this pixel wise where every pixel have a specific label. You have to take into consideration that these labels are created by humans. So we are this is level 1C and this is created by humans. So it takes us around 2 hours by point to do it properly because we do it, we try to do it as much good as possible.
Yeah, that's so, 2 hours per image, is it?
For these 5 images. So yeah,
for 5 images, it takes us.
Okay. Yes, exactly. So yeah, we spend like a very long time. I think we were a group of almost 20 persons working. So this is the high quality subset. Are all these purple points that you can observe in this map. But we also have some scribbles. So it means that we are not making labels in all the image, just in some important parts, principally at the borders and at the center of the classes. And finally, we have a huge data set as well with no labels. And why we design CloudSEN12 in that way? Because when you are looking in the literature, recent literature, I find different strategies for training algorithms, like self-supervised learning, semi-supervised learning, weakly supervised learning, the standard supervised learning, right? That uses data and you have fusion learning. So I had to cover all the different requirements that users have for training algorithms in CloudSEN12. So yeah, this is a bit the idea how we design the data set.
Cool.
Yes. So just to summarize this part is like we try to put all together and deliberate to the users using this standard and spatial and temporal data catalog. So so yeah, this is basically, I think, in a very short way what we did with CloudSEN12. Yes.
Cool. Wow. So it's a very large data set. Number of pixels, 4.5 billion pixels.
Yes, and we are currently working in a second version of the dataset. We are in the middle of this process, so we are trying to duplicate the amount of pixels that we currently have because it is even that CloudSEN12 can look a bit big, is large, but there are a lot of places where the algorithms doesn't work still well, especially in Russia. And in some places as well in the tropical. So yeah, we are adding now some points where the algorithms algorithms are not working well. So
is that something to do with the terrain there is more challenging or just smaller number of training data set?
Yeah, exactly. We are adding principally some points where the algorithms are not working well. So because this is true, we are trying to create a better balance now between images that are easy to detect close and challenging images. So this is what we are working now, and we are developing algorithms based on this idea. But our philosophy is like, if we want to use neural networks to solve this problem, we have think first in create a good data set. So this is what we are trying to do with my group in Peru.
I see. And so you're iteratively refining a model on this data set, looking at where it's failing and saying, well, that's definitely where we need to improve our data set coverage.
Yes, exactly. That is something that we also show in the paper. This is the preprint, and soon the paper as well will be available in the official version. But if you go to the paper in the last figure, we also make some technical evaluations where we compare all the different previous algorithms, and we also estimate the human label. So this is the result that we got. So basically now, we have a large data set. So now we train a simple neural network in the paper. It's a lightweight model. In fact, it's just a mobile net with a Unet encoder, and we use a simple interpolation. We are not using something too much complex. It's a model with less than 2 million of parameters. And we perform, a simple as well hyperparameter tuning and some architecture searching. And our results show us that we can obtain a model that easily surpasses the state of the art. I think you can even use Colab and you can also obtain the same results. So, and more important than that, okay, we are creating good algorithms now that we have a big data set, but we also can do it faster, right? Because the conventional algorithms that use these threshold-based approaches takes around more than 10 minutes most of the times, but with this kind of neural networks, at least these lightweights, we can obtain results in less than 1 minute in some, depending on the number of parameters of the architecture. Because if you are using maybe something more complex, it will take more time, but you can as well obtain better results. So we are now in this second version that I mentioned to you. Try to create a good trade-off between these two different features, and we are also trained using these quantified versions. Instead of using float 32 bits in the weight, we are trying to only use 8 bits, so it makes even faster the algorithms, but you lose some accuracy. But yeah, this is some ideas that we are currently exploring. But this is, I think, the good about CloudSEN12, and just a visual comparison to people that is listening this talk is like, this is, for instance, the results in Sen2Core. I think if people was working with Sen2Core, one of the characteristics that always happen around the world is like, it have a lot of problems to detect close shadows specifically. So you have problems here. You have a lot of false positive in high altitude areas like the Andes in Himalaya, for instance. But these are more or less the results that we obtain with this simple neural network. As you can observe, the model can do a really good job detecting these close shadows. So
yeah. Is it processing the whole image at full resolution, or do you resample to a low resolution?
No. We are processing at 10 meters, but we make a chop. We have the complete Sentinel-2 scene, and we pair in four image patches of 6,000 by 6,000, because there is an overlap between. This is a good when you use a simple neural network, because if you use a very large neural network model, it will be hard to to make prediction in large patch, because it's very memory hungry. So, but yeah, there are. This is quite important. At least something that we learned in cloud detection is like, it's important that you make prediction in very large image patch, because there are a kind of spatial correlation between the clouds and cloud shadows, and the neural network can learn about that. So if your patch is really, really small, your model will not be able to detect that. But if you are making, prediction in a 6,000 by 6,000 pixels, probably the model will catch better this correlation between clouds and cloud shadows. So it's important in the predictions, in the inference times, to not make prediction in very, small patches. The idea is try to use the large as possible for your memory. Well, but it depends on your requirements as well.
And does it use all bands of Sentinel-2, or is it only using a couple of bands?
No, we are using, at least for this experiment, all the bands, but we also noticed that, this Sentinel-2 satellite have some additional red bands. So yeah, we are looking, we observe that if we are, take off some of these bands, the accuracy don't reduce. So probably in the next versions, we are gonna do this, but it is part of our research right now.
Yeah. So, yeah. Okay. And is the plan to make this widely available as a service, or is it open source? Or?
We are in this conversion. We are trying to offer a product. We are, at least my ambitions, I think, of all in the team is try to make prediction at global scale, because I think our objective right now is try to create an algorithm that can make prediction in less than 20 seconds, and as you mentioned, it not work at 10 meters. maybe 20 meters. This is something that we are exploring right now. But because the idea now that is you are thinking to develop an algorithm that it will be, at global scale or a large scale, you have to start to think in all of these details as well. But yeah, this is something that we are exploring right now.
Fantastic. Yeah. Okay, so the paper's coming out soon.
Yeah.
What's next for yourself as well then?
You mean after the publication of the paper? Yeah. As I mentioned it, we were working in this second version of CloudSEN12 because something that we when we develop this dataset is like not a monolith. It's like no, okay, we create a dataset and the paper is published and that's all. And our idea is, okay, we create a dataset and now we are doing versions just to show a bit about that. The dataset right now have a size of 1 terabyte of size, and the version that we published is the version number 1. But one of the problems when you have humans in the process of something, the humans are always biased and humans always make mistakes. So we are always looking at the label list that we provide, and we observe that there are some images. I will download this. But we observe that there are some images where the human label is not good. So this is something probably we are gonna have to iterate a lot. So in the version 1.1, what we did is like, okay, there are some IPs IPs we call to these image patches where the labels are not okay. So we relabel, and yeah, here there is a small report about the changes that we did. Okay, here probably the thin clothes are not correct, so we change it. So because this there are 10,000 images, so there are some images that probably always gonna have some mistakes. So we are always trying to improve our results, and because this is the only way to really solve the problem. Because publish a paper, I think is easy, but if you really want to help or help in move forward the progress on, in this case, I think it's a bit small, the cloud detection part, but yeah, I think it's like you have to iterate, right? It's like it's not create a monolith. It's you have to create. It's like create software. This is what I try to say.
Yeah. And for tracking the data set, are you using any particular like tools like DBC or anything? Or?
I think it's a good question because I think one of the keys of success of the dataset is the labeling tool that we use, and I would like to thank to the creators of these tools. The name is Iris. It was created for the SFE lab. Maybe I can show an example about how to use Iris, because I think you can use Iris for any. If you are trying to create labels for a small project about that is related to semantic segmentation, and it's quite simple to install. It's here, for instance, this is it's a Python package first off. So you only go to Iris fill up. It's as well in the website of CloudSEN12. If you go to the website and go to here where say repository, there is a link where with the version of Iris that we use, and also in the paper we mentioned it, I think, many times. Okay, so you have the package here, and it's a Python package. It have very generic three-party Python package. So I think you will not have any problem to install if you have installed in your computer Raster.io. That probably because it have some GDL dependencies. Maybe it's the hardest package for install, but if you have GDL, you will not have any problem.
Okay.
So it comes with a demo folder. So in this demo, you have this JSON file. I will enter to this JSON file, and this is the structure about the project that you can. This is how you have to structure your project for make the semantic segmentation. The idea is like you can create a new folder. In this case, they call image, but you can put the name that you want. And this is the important part, is like you have the ID. So the next folders, it's represent a different image. So it should have a different ID because every folder will represent this different image. So and inside this folder, you can put all the data that you consider. In this case, in this demo, they consider Sentinel-1 and Sentinel-2, but if you have other kind of information, you can put it as well, and you just have to declare in this part. So yeah, so this is about the images that you define. You can use any format because it uses Raspberry I/O in the bucket. So if the image can be read by a Raspberry I/O, you will not have any problem. You can also put some thumbnails. I will show you why, but this is not mandatory to put this information. And this is the important part, I will say, that is the semantics that you will create where it will be saved. So you put the path, and if you put here RGB, the result will be saved in well, I forgot the name of this format, PNG. Yeah, PNG. Yes, and the mask area. So I think it will be easy to explain it if I run the code. You just open a terminal. Oops, I create a folder. You just have to open a terminal, and you only have to script iris label. This is the function, and you have to put here the name of this the main project that is this JSON. So write here up demo because it's inside this folder, and that's all. So it will ask you for create a password, and it's in fact a Flask server.
Okay.
So you only have you can create an account here. And that's all. And you can start to create the labels, and it's quite nice because you can add many different. For instance, here you can add other panels, and for instance, I want to have a better context about this. I have as well some web maps that permit me easily.
Cool.
Yes, and for instance, I have here. This is why they need this thumbnail image, because you can put it here, and if you click here and show me on the map, it will also appear the image in the map.
Nice, nice.
So, and what is good about Iris, and this is why I really love it. I will work in. This is something that I also have to do, is improve that documentation, because it's a really cool tool, and it just an adaptive learning system to create the labels. I can show you really fast about that. For instance, I want to perform the labeling part in this image. So the only thing that you have to do is create some pixels where with respect to the class, right? I will add just some of them, and now you here probably there is, you don't have too much contrast, but if you use these snow bands, you will have better contrast. And how you can define this is in the JSON file. In this part, you have a code called view, and in views you can define any different combination that you want, and even you can use some functions that like edges that Iris offer by default. So you can use it. For instance, if you only want to show one specific band, you can define here the color band. Or if you want to define a composite RGB visualization, you can put here the bands, and that's all. I think it's quite simple to use. And now, for instance, I will add here, because this is a cloud, right? So I can change, if I click here, I can change the semantic class that I want to define. But you can also use a number because it has a lot of shortcuts. And yeah, you can increase the size of the brush, and yeah. So what is a good thing, as I mentioned, is like you have this AI button. So if you click in this AI button, it automatically will create the label for you, because there is a AI in the middle. So this is why we were able to create so many labels, because we have this machine learning support. So yeah, this is the idea. Obviously, it's not perfect, but the idea is like, okay, now I will add some pixels where the model was not doing good. And for instance, I can improve a bit the border to help you to recognize better the borders. And I can rerun the algorithms again. And now the result will be better. So this is what we explain in the paper. I think I have something here. Yeah, this is a bit the idea. Okay, we are gonna iterate many times with the machine learning algorithms until we got more or less a good result. And after that, the final step is make final manual fine tuning. So this is how we create the tools. And yeah, I think Iris is for sure one of the best tools for create labels. So if you are thinking to create a data set, for sure, I think it will be nice that you can give an opportunity to Iris, because it's really, really worth it. Yeah.
Looks like it's got some great features, many that I sort of tried to hack together myself and other tools. But if I'd known about Iris, I could have saved a lot of time and tears. So that's really a good introduction. Thank you.
Yeah, and for instance, what we did, and because as I mentioned, Iris use raster IO. So imagine that you create a data set. Imagine you have a lot of different Sentinel-2 images. You can save it in a Google Cloud Storage bucket, and you can directly read it. You put Iris in a virtual machine in Compute Engine, for instance, and you can directly read it from this Cloud Storage, and then you can simply save the result, because if you click here, the result will be saved. So you can send it. So you don't need, create a virtual machine and put all the data set inside the virtual machine. You have in different spaces, and this is good because and this is possible because Iris use, as I mentioned, this raster IO package is very, very great. So the results are saved. Right now, the result will be saved here, bro. Sorry, we are in Mountain, so it's here. It's a PNG, but you can also save it in a GeoTIFF file if you want.
Wow,
this is really more or less. Yes, this is a bit about Iris. And
cool.
Yeah.
All right, I'll put the link in the show notes at the end so people can find Iris as well. Thanks so much for the presentation. Where's the best platform for people that want to follow your progress?
Okay. Yes. And let me share the name of the website that we currently have and maintain is CloudSEN12 Spanish time .github.io. So in that website, you can find where exactly download the dataset. The dataset is currently in Google Drive, but you can also download it from Bank data. And we have a lot of different examples. We have examples about how to download the data using Easy Stack, how to run neural networks, how to visualize the data in Google Earth Engine. And yeah, there are so many different. So if you are interested in the project, just go to the website, or you can also write me a direct message and I will reply you as soon as possible.
Fantastic. That looks like a treasure trove. I'm sure I'll be on that later on. Well, thanks so much, Cesar, and I'll catch you next time.
Okay, thank you for the invitation and have a good day. Bye.
Bye.